So hi everyone. This is a lecture on Bitmask DP, Range DP, and Digit DP. So we'll be discussing some theory along with problem set that I had sent on the Discord group. So first we'll begin with Bitmask DP. It's a very useful technique, especially when it comes in OI, because you normally have subtasks like the small subtask n is less than equal to 20, which normally uses some or the other bitmasking technique. So we'll be starting with Bitmask DP first. So you must have seen some DP problems in the previous lecture. So normally you would always have a DP of something like, let's say, n, where n is normally an integer, or the a position in an array. But now we see that this state of the DP, values n is here. We can actually, it can be anything. It can be a range of a contiguous range of an array, or it can even be a subset of elements. So bitmask DP is where the state is a subset, where you can choose to have some elements and also choose to not have some elements. So an example would be, let's say, this is a set, and then let's say some subset A of this is, so we have chosen the elements 2, 4, and 8, and then like we have omitted all the other elements. So 2, 4, 8 is a subset. Yes, 2, 4, 8 is a subset. So now we solve the problem for DP, basically DP of A, where A is actually a subset. It's not just a single integer. So we solve the problem for this subset based on subsets of this subset. Let's say DP of A depends on maybe DP of B. Like normally in a normal DP problem, DP of N would depend on the smaller DP, like maybe DP of N minus 1 plus DP of N minus 2, as in the Fibonacci sequence. Here DP of A would depend on the smaller subsets of it. Like maybe it would be the summation of DP of 2 comma 4 plus DP, sorry, plus DP of 4 comma 8 or something. So you get the idea, right? It's just basically you're doing DP on subsets of an array. And actually we don't actually, like in implementation wise, we do not actually store the entire subset as it is. That's a very convenient way using bits. So now we'll look at how to store the subset using bits. So initially, let's say we have 8 elements, right? Here they are just 1, 2, 3, 4 up to 8. And let's say we want to represent this 248 in a more convenient form. That's more convenient. We don't actually store 248 in a DP array because it's also inconvenient, and also it requires much more memory and it's very slow. So the way we represent it is using bits. So 1 is not in this subset, so it corresponds to a 0. 2 is present in the subset, so it corresponds to a 1. 3 is not there, so 0, and so on. So you can see that the number that this subset will represent is something like this, whatever this number corresponds to in binary. So this number corresponds to, yeah, the sum of these. Hope I'm not wrong. Yeah, 81. So basically 81 represents this subset, because in 81, the binary representation of 81 is 0, 1, 0, 1, 0, 0, 0, 1. And here basically the last element, 8, the 8 bit is set. So actually what I've done is I've inverted the bit, but I mean the argument is still the same. The 8 bit is set here. We do not have 7, we do not have 6, we do not have 5, there is 4, we do not have 3, and then there is 2. So this is how we store subsets. So any questions till here? Okay, someone asked what is a Bitmask. Okay, so basically it is a way of, it's like representing a subset of something where um, you use bits to represent whether something is present or not.
So, could you explain that in more detail actually?
Okay, yes. So what exactly do you want to know? Like how the elements are used?
Yeah, so maybe you could make it more clear how you can assign a number to each subset, and how exactly that number is assigned.
So you want me to give another example for this subset,
Yeah,
like a different
perhaps
subset?
another example. Yeah.
Okay. Can you give me a subset that you would like to know the number for?
Okay, yeah, maybe you could write 2, 3, 6, and 7.
Okay. 2, 3, 6, and 7. So I'll again write those numbers again. So you said 2, 3, 6, and 7. So again, we do the same procedure. Here, we do not have 8 in the subset. So below that, we will have a 0. We have 7. So below that, we will have a 1. We have 6. So we will have a 1, 0, 0, 1, 1. So you know how binary. So I'm assuming everyone here knows how binary numbers work. Like if somebody does not, I can explain. Okay, people say they know. So now, can anybody tell me what this would correspond to in binary, like binary representation? You can type it in chat. Yes, it is 102. Avigna, I don't understand your question. What do you mean? What is it in base 10? It is 102, right?
Yeah, no, I just stated the question in another way for the others.
Okay, is it clear now?
Yes, it is clear.
Okay, so this is a convenient way of representing subsets instead of actually writing something like dp of 2 comma 4 comma 8. I mean, this is very inconvenient and also slow. So we would just write dp of 81, because 81 is essentially mean the same thing, and it's a much more nice way of representing. We can also do bitwise operations on it to remove things like basically set bits and unset bits. So it's just a very convenient way of representing subsets. That's what I was explaining so far. So is that clear? Somebody's asking, is it better to convert this binary representation into base 10 or use bit set for reference updates? At least in the problem that I've seen involving Bitmask DP, they use it in base 10 because that's what you store in a DP array, right? Like df of n or dp of n. So it would be more convenient to store that subset. I mean, there are cases where you use bit set, but I don't think it is to store subsets. Bit sets are generally used for speeding up solutions, like to fit in non-efficient solutions, sorry, inefficient solutions. Okay, now we'll move on to the next thing. So now we can actually add and set bits using bitwise operators. So let's say we have a subset like this, 10010, something
Okay,
like
okay,
this.
sorry to interrupt, but I think someone in chat has another question.
Who's that?
Nehul asked how 81 is the
So I'm
answer
not
to
sure if
80.
my calculation is wrong, but I think it should be 81. Okay, the, Nehal, do you understand that this can be represented as a number in binary, right? Okay, you missed some part. From where did you miss? Okay, so Okay, I'll just go through it again. So let's say we have a set like this, and we want to basically do a DP on it where the states are the subsets. So, like say, let's say we want to calculate DP is where you solve sub problems. Smaller problems are merged into larger problems. So you break a bigger problem into smaller problems. You solve the smaller problems and then you combine them and get the answer for the larger result. So here, instead of calculating the answer for this entire big set at once, we would actually solve for each subset and then finally combine it to one. So let's say at an intermediary state, we are just solving for the subset 2 comma 3 comma 5. So I would write it like this: 1 2 3 4 5, and we in this subset that we're solving for right now, we only have the elements 2 3 and 5. So we would actually, what we would do is we would put 1 in those places, and even the remaining ones which are not there, like 1 and 4, we will put a 0 below them. This is just a convenient way of representing the subset. And you can see this is a number in binary, right? And it's unique for each and every subset. So again, this would correspond to 2 to the power 0, 2 square, and 2 cube. Whatever this adds up to, that would be the value of this subset. Okay, you got it. Okay, so this is, I just explained a convenient way of representing subset that is using bits. And bitmask essentially mean that where you use bits to represent something. You mask something in the form of bits. In this case, it's subsets. So now we will notice that like we'll look at one more way in which these subsets are convenient. So let's say we are right now we are solving for 2 comma 4 comma 8, like any random subset. I just chosen this because I know the value dp81, and maybe it depends on smaller subset. That's what DP is, right? A larger problem is dependent upon smaller sub problems, and then you consolidate them together. Let's say the answer for this depends on the subset 2 comma 4. Of course, the answer that it would depend on would be a proper subset of it. That's mostly the case. And plus some property related to 4 comma 8, and some property, let's say 2 comma 4, 4 comma 8, and 2 comma 8. So basically, in this case, the DP is formulation is just DP of S. Any subset S is basically DP of S for all X belonging to S. So basically, the DP of a subset S is basically the summation of the DP of all the subset of S which have exactly one element different from the set you're calculating for. I mean, I'm just taking a DP here to explain how it works. Or if this is not clear, I can explain in depth. Or is this fine? Okay. So now again, we would also like to, you see this operation here, right? We're removing this X from S. And again, it turns out that's a convenient way using the XOR operator. So let's say right now we have 81, and X is maybe, let's say, the fourth element from 2 comma 4 comma 8, which corresponds to 81, and we want to convert this 81 into just say the subset 2 comma 4. So we want to basically remove the eighth bit, and this is very easy with the XOR operator. It is just 81 XOR 2 comma 8, and since 2 comma 8 is already set in this, sorry, you said 2 comma 8. Yeah, it is 2 comma 8. So just XOR 2 comma 8, and then that bit would get set off. So that bit would become unset. It would become 0, and that would just be, so the corresponding value of 2 comma 4 would be 81 XOR 2 comma 8, 2 to the power 8. Does this make sense? I'm assuming all of you know how the XOR operator works. Okay. So this is basically convenient notation for Bitmask DP. And now I would like to stress that Bitmask DP is very useful, especially in OI, because normally the problems have a lot of subtasks, and normally the subtasks are like n is less than equal to 10 to the power 5 or something, and then you would normally have a subtask that looks something like this: n is less than 20 or n is less than 23. So this n is just It's too slow for a factorial solution. N factorial would TLE, but it is just enough to pass something like, let's say, 2 to the power n, O of 2 to the power n, or O of 2 to the power n into 2n. So these would pass. And this generally uses some sort of bit masking or bitmask DP, a brute force. And this normally shows up in almost every problem, especially where it's a dynamic programming problem or something. We don't normally have a subtask like this. So knowing bitmask can help you like gain points, especially in ZC or INOI. So bitmask DP is like very helpful to know. That was just one side point. So the like bitmask DP is also very easy to recognize because as I said, you would normally have constraints like this, like extremely small constraints, n is less than 20. So it's very easy to recognize such problems as well. And the time complexity usually looks like, let's say, n into 2 to the power n, or maybe in some rare cases n square into 2 to the power n. You would actually go through all the subsets, and in each subset the transition would probably be like O of n. Like in this case, you can see that from a sub for this particular DP case, we are basically, the transition is basically this. So this would be O of n on average because you're removing every element from the subset and you're calculating the individual DP values. So this would be the no, like this is how the complexity usually look. So now if the idea is clear, I would like to go to some basic problems. Yes, Avigna has a point. Subtraction is also quite good. And you can also turn on a bit using XOR, right? If it is set off. Yeah, if somebody has a difficulty understanding XOR, it is basically just adding the bit. You're just setting that bit. Aditya, I'm just using an example to show. I just consider an example. Okay, actually, I think I made a mistake. It's not 2 to the power 8. It's 2 to the power 6. Avigna, why are you saying it should be 2 to the power 0? Yeah, actually, I messed up the order. So basically, whatever bit that corresponds to, you remove that bit. So here I took the order from right to left: 0, 1, 2, 3, 4, and 5. So I'm removing the bit. Like suppose I want to remove this and get a subset, I would remove whatever bit this corresponds to. Yeah, I made a mistake saying it right. I forgot that we're going from right to left. I hope it's clear now. Like if you have something like this, a subset like this, and you want to get a subset without the last element, then whatever position this was, let's say 2 to the power I, you would XOR this value. Let's say this has a value of x, then this would have a value of x XOR 2 to the power I. Is it clear? Okay. I'm sorry for the mistake. So the first problem that we'll be looking at is team building. I've sent the problem, the group. I'll again send it in the chat. I hope everyone's opened it. Actually, I'll discuss the CSCS problem before that. It's more introductory. I'm discussing the CSCS problem first. So you guys can just take a look at it, and if you have any ideas, you can type it in the chat, and then I'll discuss the solution after like 2 or 3 minutes. It's a very easy problem. Shouldn't take you more than that. We're doing the CSES one first. It's a standard motivation problem. For those of you who are doing Bitmask DB for the first time, I mean, just try to think of something in terms of subsets. You can see that n is less than 20. So try to think of doing DP of a subset in terms of smaller subsets of it. I'll take a solution in 2 minutes. If you have any ideas, you can type it in the chat. Okay, there are some solutions in chat. Someone is saying I got an n square into 2 to the power n. Can you share your solution? Yes, your DP state is correct, but why should it be n square into 2 to the power n? I don't see why n square. And you're claiming that it will be a Hamiltonian path. I mean, how do you ensure that it's a Hamiltonian path? What are the transitions? You don't need it to be a Hamiltonian path. You can. No, he's saying Hamiltonian path. I don't understand because of Hamiltonian thing. Yeah, the transition would be n, so it's n. If you don't know what Hamiltonian path is, it's not relevant here. It's like it's not relevant here. You don't need to. I don't think you need it. Okay, I'll press in the DP here. So you can see that n is quite small. It's just 20. So it would hint at some kind of bitmask DP. So what we can do is we can define for a subset, like we want to visit all the nodes in the subset. Let's say 1 to n is the subset of, like, basically we want to start at city 1 and then reach city n at the end. And we have these subsets like this. So we will solve the problem for any random subset, like let's say 2, 4, 5. And we'll see how the answer for this depends on a smaller subset, say 2 comma 4. And we will also, and since this is a graph, we need some kind of information on where we had ended in the previous subset. You're saying Hamiltonian, but is it necessary that it has to be a Hamiltonian path? I mean, I'm not sure. I'm just asking. Is it necessary that it had, because I don't use that fact. I think, at least not explicitly. Let me think about it. Okay, sorry. The flights are all one way. Yeah, yeah. Sorry. The flights are one way. I just didn't think about it explicitly that it would be Hamiltonian. Okay, so here we say that dp, yeah, we say that dp s of I is basically the number of ways to visit all the nodes in the subset S such that we end at node I. So this is the state that I'm defining, that the number of ways to visit every single city in S such that we end at city I. And the transitions, like, let us see, as I took the example here, 2 comma 4 comma 5. So like if we analyze this case, we can only visit like these cities in like a limited ways, right? We can go from 2 to 4 or something and then go to 5, or 2 to 5 and 4, something like that. Like what I mean is we can isolate one node, and then we can take subsets of the node. We can take subset of the subset such that that node is not present, just removing one single element from that. Does this make sense? Like we come from a previous subset and such that we come to this subset. Yes. So it would be something like, okay, I'll just write the DP transition first and then I'll explain. DP without the X. So I'm writing S minus X here. So it means without the X. And then, sorry, without the I. So because we want to end without the I. And then X, such that there is an X in the graph. So that graph I is connected to X in the graph. So I mean, it's not very easy for beginners. So I would suggest you to take some time to think about it. You have a subset like this, and you're let's say you have picked a node that you're going to end at. So what we want to do is we want to, of course, that node cannot be there in the path that you're solving the subproblem from. And then also you are iterating through all the smaller subsets without one single node in that. And then it provided that there is an edge from the node that you want to end at and the node that is ending at the previous problem. So you can kind of combine them and you get the new DP state. Does this make sense? There is an edge from I to X. Yeah, there's an edge from I to X. Yeah, it's I to X. Okay, I'll take an example. I'll actually take the sample. So this is the graph given in the sample. What if the degree of vertex is different but out degree is different? Will it be considered two paths? The problem is just asking us to find the number of paths from 1 to n. I don't understand your question.
Like in this your graph,
Yes.
one is also going to two, and then two is going to three, and then
Okay.
again to four. But over there also it's going all to three, and then to four, and then again to there. So will we
Yes.
consider two paths? Like
Yes, it
if
is two paths, of course.
nahin, in this question, nahin, then okay. Then we will
It
not.
is a different path.
Got it.
Otherwise, what you're saying, you'll only have one path from 1 to n. Yes. I hope your question is clear. Okay, so now the base case for this is the base case for this would be yeah, I think it would be this. Yeah. So basically, the number of ways that to cover only the first city. You're already at the first city, such that you end at the first city is basically one. That's the number of ways you can reach. And now let us say that we want to calculate for to visit all the subsets. I'm not using the number notation because I want to actually explain the concept. So let's say 1, 2, 3. dp of 1, 2, 3. This would be summation here. I hope you understood that. Let's say we want to calculate number of ways to visit all the sets in 1 to 3 such that we end at 3. This would be 1 minute. Let me just think of the dp state. This would be the number of nodes in 3 would be 2, comma 4. Such that x is also a part of s. So 2. Can you just give me a minute? I'll just think of the states. Yeah, so this case is a little confusing because there's only one case. I was trying to think of something else. So in this case, it would just be this, because that is all you can do, right? Because you can visit 1 to 3 by visiting 1 to and ending at 2, and that since there is an edge from 2 to 3, so that's only one way you can get there. Does this make sense here? Like the number of ways to visit all the nodes 1 to 3, such that you end at 3, is to visit the number of ways to visit the nodes 1 to 2 and ending at 2, such that you go from 2 to 3. Okay, that's also an edge from 1 to 3. Sorry. No, sorry, that would be included. Yeah, this is the only way. Does this make sense? Whoever asked for an example. Yeah, like there was only one case here. I was trying to search for something else. So now I'll just formulate the problem. Like I'll just write the solution formally. So if you understood this, it is DPA transition, you can just say yes. If you didn't, then I'll try to answer your doubts. Like there's not really much to explain in this. The number of ways to visit a subset S such that you end at I. So basically, of course, I has to be a part of that subset. So you remove I from S. So this is the subset, the set that you get after you remove I from S. The number of ways to visit that such that you end at X and there exists an edge from X to Y. So does this make sense? If you have any doubts, you can ask. You're saying please explain. What part did you not understand on about this? Because it's just classic DP. You're just going through subset. I mean, the notation is a little confusing. I got confused a little bit. Can you tell exactly what part you did not understand? Yes, because you have basically n square states. Sorry, 2 to the power n into n states, and each transition is n. So this would result in a total time complexity of n square into 2 to the power n, worst case complexity. You can see that number of subsets would be 2 to the power n, and we're choosing one element from this, so the number of states itself is 2 to the power n into n, and a transition, basically you can choose to remove an element such that there exists a graph from I to x. So you can have again n transition, so that would be n square into 2 to the power n. Okay. I understand it might not be very intuitive for the people learning Bitmask DB for the first time. I tried to formalize it. I mean, that might make it a little more confusing. So if you can understand it with words, that DP of SI is number of ways to visit all the nodes in the subset S such that you end at I, is basically you remove I from that set and then you solve for the problem such that you end at X such that Okay, I'll try to explain it like this. Let's say we have some graph like this and stuff. I'll take a simple one to explain. Let's say we have this and we want to visit every single node and we want to finally end at this node. So now we want to visit nodes 1, 2, and 3. So our subproblem now reduces to finding the number of ways we visit 1, comma 2, and such that we are ending at 2. Because when you're ending at 2, we know that there's an edge from 2 to 3. So this is the valid path. So that would directly be a link to 3. So that was our condition here, such that there is an edge from 2 to 3. I hope it makes sense. Okay, now we can move on to the next code for this problem. This is slightly harder. It has another element to it. So I'll discuss the problem after 5 minutes. So do give it a try. The idea is quite similar to this. And if you didn't understand this, like just try to think about it once again. I'm sure you'll get it. Just try to think about it in terms of subsets of the subsets. We'll discuss the problem at 8:50. Okay, so I'll discuss the code for this problem now. If you have any ideas, you can write it in chat. Like it's not a very easy problem. I think it's quite high rated. So if you have any partial ideas, I'll try to answer them. Anybody, any ideas, anyone? Again, it should be obvious that it is Bitmask DP looking at the constraint here. Actually, it's a little bit of a different Bitmask TP because here you have p is less than 7, but n is quite large. Okay, I think no one has any idea, so I'll go to the solution. So this problem is, as I said, it's quite hard, like at least compared to the previous problem. The idea is similar though. So what I will do is I will first solve for a like easier version of the problem. The problem here is like almost the same thing, except here you not only have to select players for the positions, but then you also have to select them for the member of audience. So it's not a very straightforward problem in terms of Bitmask DP because of the member of the audience part. If it was just if that audience part was not there, that AI part was not there, then it would just be a straightforward DP problem. I hope you're able to see that. If you're not able to, you can tell it in chat. I will explain how. Okay. So uh, now again the DP state for this is that so has everyone understood the problem statement? If do you have any problem in that? I think the problem statement is well worded. There shouldn't be any difficulties. If you have any problem, I'll explain the problem. Yeah, right now I'm just giving a solution to not consider audience. Does everyone understand the problem? Okay, I'll assume you understood. So now this is like a very straightforward DP problem. Now this mask refers to the positions mark, not the number of people, because you can notice that there are n people. Like n is like 10 to the power 5, which is huge. Obviously, you can't bit mask over there, but the position is number of 7. So the DP says that let's say we have 1, 2, 3, 4, 5, 6, 7 players. Now we're like solving a DP for 4. Let us say we want to place these 4 people, and we have, let's say, uh, 3 positions mask like 1011. Let's say there are only 4 positions, and then we are solving for the mask basically DP of 4. So we want to place these 4 people into these 3 positions exactly, first, third, and fourth position. And we want to do this in such a way that we get the maximum possible strength, and disregarding any audience member, we just want to choose people for the position to play in. Does it make sense? Yes, Avigna, whatever you're saying is correct. Okay, someone's asking me to explain the problem. So there are n people, and the n is huge. Like there are 10 to the power 5 people. Like up to, there can be up to 10 to the power 5 people, and then you have p players playing in p different positions. Like in football game, like you would have a different position. So you want to allot some players to these positions, And some people you don't need to allot them as players. You can allot them as audience member to cheer. But each of them in their roles they contribute some amount of strength to the club. And the if you put the IR person as an audience member, he will give AI strength to the whole team. And if you choose a person I for a position J, he will add SIJ strength. You have the freedom to choose whether you have the freedom to choose any person for any position you like, or you can just place him in the audience, or you can choose him for neither. And you have to do this in such a way that you maximize the maximum possible strength. Is it clear now? Okay. So now I'm solving the problem without the audience member part, because then it would just simplify to standard DP. So I'm doing without the audience member part. So let's say we are solving for DP4. So we have the first four people, and remember there is no audience here. So we have first four people, and we want to place them in and you can place them in any position. And I think the problem is that each position has to be filled. Yeah, they have to select exactly P players, one for each position. So we have to choose at least one, like every position has to be filled. So now let's say we are only considering first four people, and we want to choose any three of them to play in positions 1, 3, and 4. And the players also have SIJ. Like basically, if you choose a particular player I for a position J, then he contributes some particular value. So we have four players, 1, 2, 3, 4, and these positions 1, 3, 4. We can place them however we want. And now let's see how this transition actually works. If let us we have the choice, right? We can either choose the ith person, like basically this fourth person that we're considering, and we're choosing the first four people. We can actually choose him, or we can not choose him. We can do whatever is optimal for us. So DPI of mask would be so now what we do is we are basically we have the answers. We go in increasing order of the number of people. So we have the answer calculated for literally every bit mask for 1, 2, and 3, and we want to use that to calculate the answer for 4. So that is how we are doing. So we know the answer for 1, 2, 3. We know how to place 1, 2, 3 in literally every possible configuration of positions. We want to use that information to calculate for 1, 2, and 3, 1, 2, 3, and 4. So you can see that DPI mask depends on DPI minus 1 and some changes to mask, because we are removing a person and trying to see how he fits in, and then we're adding that value also. So that's how this works. And since we are removing that person, then here we would have a term that is adding the ith. We are adding that person, right? So he would contribute a strength to the team. That would be Si of j. So we are solving for the problem for the previous I minus one player, such that that player is not there, and we're choosing him to add him for this current DP state. So he would contribute a strength of Si comma j. Does this make sense? This is like Bitmask a transition. And considering that we are taking him, otherwise the answer can just be maximum of this, or we can just not choose him. It can just be DP I minus mask also. If this makes sense, can you just let me know? Okay, so this is standard problem of you just want to choose some number of people for some position such that you want to maximize the score. But if when you're not choosing a person for any position, you can also choose him for the audience. So now this is not exactly Bitmask part. It's a hard part of this problem. So here we can do a greedy thing. We can sort all the people. Like right now, I'm just doing them in the order that they're given in the question, right? Person one, 2, 3, 4, 5, 6, 7. What we can do is sort them by their AI, basically their strength that they contribute to the audience. And I would now do the DP on that sorted order of people. Like the person with the highest audience strength would be in the starting, second highest, and so on. Now the advantage of this is that if in like any particular DP state, if I choose to not take a person for a position, then it would always be optimal to take him as an audience member because they are in increasing order. Like if I do not take him for an audience member and if I take someone else later, this would definitely be more optimal because he has a higher contribution to audience strength than the guy later. So this is the advantage. So I sort them by AI, and then I would take this guy. If I'm not taking him in position, like I would handle this in the transitions. If I am not taking him for the position, then I would add him to the audience member. Does this make sense? Like we are sorting by AI, and then so the advantage of that, so that if we are not taking him at the position, we can take him as an audience member. Or if this is fine, then just let me know. Okay. So now I'll write down all the transitions that we have discussed. The problems is this is the considering the position, right? Right now I'm considering that if I'm taking him for a position. So I can go through all the maximum things that J is set in the mask. So this is standard DP. So I will take the maximum of all the J that J is set in the mask, right? And clearly the base case is DP of 0. Like you can try to think why. It's not that hard. You will easily get it. Why DP of 0, 0 is 1. You can see from the definition of what DPI mask is, you'll easily get. And now I claim that it would always be optimal to take the person. If I'm not looking for a position, I will take him for the audience member. But after some time, we have fulfilled our criteria to take for the position and audience member, because if you see the question, we can only take k people for the audience. So now this is also very easy. As Avigna, I think he had said in the chat, we can keep the track of total number of people chosen without needing another variable by just doing built-in popcorn mask. Exactly right. So we can easily check if right now we have some space for audience members. If there is any space for audience members, we always consider them, because as I told you, if we do not consider them, then it is not optimal, because it's always optimal to consider the person right now if we have any quota left for audience members. So that can be handled by seeing how many bits are set in the mask and the value of k given in the input. So right now I'm talking about this position. So we can choose the maximum over all this. And if we can use a person, if we can allot this guy to the audience, then it would be, we would also take the maximum of DPI mask is this would, like, you would add this on, you would only add this guy to the AI strength. You wouldn't use him for any position. You would not he would not have any Sij contribution. You would only take him for the audience. And the answer would just be the bit, you would want to consider all the people. Of course, it's optimal to consider all the people. And you would, like, the bitmask would be such that all the people are set. All the p positions are chosen, because you have to fulfill all people, and in between the number of k audience members will like automatically be satisfied because of our transitions. So this would be the answer. And the time complexity of this will be that we have n state here, n, we have 2 to the power p, and then in each transition we are going through all the bit mask, all the bits set in the bit mask. So there can be at most p bits. So the time complexity would be O of p into n into 2 to the power p, which you can see from the constraint that this would very well pass under the time limit. Do you have any questions on this? Like I had not explained some parts, I had left as exercise, like this base case stuff. You can easily try to prove them. Yeah, it's a very nice question. That especially the greedy part of using audience members is a very nice part. And Avigna, you said that you can keep track of total people. How did you get that idea without the full solution? Okay, that's why. Like, I mean, that's not the first thing that you would realize. Okay. Is everything clear till here? If you have any questions, you can ask. This position part, if you want me to explain, I can explain again. I think the audience part should be clear. It's just simple greedy. You sort them by decreasing, non-increasing order, and then you just keep taking. If you can, if there is space for audience members, you just keep taking them. Okay, I'm assuming everyone understood. Now we can move on to range DP. Range DP is also very nice. Basically, in the DP states, instead of having subsets, you have continuous ranges of the array. You solve the problem for the range based on smaller ranges that are contained inside the range, and you add the answer. It's very analogous to Bitmask DP. Instead of subsets, you have continuous ranges. So you would that normally the states look something like this: DP, L, R. So basically, you solve the answer for, let's say you have an array like this, 1, 2, 3. You would solve for a subarray like this based on smaller subarrays contained inside them, or something like this. You would solve for this, you would add the answer, and that is what range DP is. The time complexity is usually O of n cube. Later, if you do some advanced studies, like you'll see that there are some optimization to get this to n square in some special changes of range DP, but generally the time complexity is O of n cube. Your n will be less than 100 or 500 or something, so that n cube passes. So it's typically mean that it is range DP. Mostly it is range DP. You can guess that from constraints. So do you understand like how states are used in range DP? Okay. So now I will take a problem. This is an code for this problem. It's quite easy if you like have worked with palindrome. Then it's very easy. Do give it a try. Like normally, I mean, I'm telling that states can be generalized. They don't have to be a single number. They can be a continuous range, or they can be a subset. That's what I mean. Like states are basically continuous ranges. So I've sent a problem in chat. Do try. It's very standard, and like it's a good introduction to range DP. The transitions are also quite simple. I'll give you 3 minutes. If you have any ideas, please put them in the chat. I will try to confirm them. Yes, your state is correct. What will be your transitions? Okay. Why do you think you need two DPs? I think the state that you mentioned above is sufficient, at least for this problem. Okay, you're calling that a DP. I mean, it's just a Boolean array, right? Okay. Yes, Avigna's hint is correct. Like it's only the only key idea to solving the problem. Uh, Not Jarvis. That is one correct transition, but I think you're missing out on two other transitions as well. Like that's not the only case that you need to add. The transition is not very simple. Okay, I'll go to the solution discussion now. So now the key observation is that if you see that the substring L to R position, the string basically from position L to position R is a palindrome, that would imply that uh, SL, that means the characters at position L and R are equal, of course, because that's how a palindrome is defined. They read same forwards and backwards. And also the recursive observation here is that the substring L plus 1 to R minus 1 is also a palindrome. So this is the key idea. So let me take an example to, if it's not obvious to you, then something like this. This is clearly a palindrome. So we see that if this is a palindrome, that would imply that these two characters are equal. And then this string right here, the inner string, excluding the two outer characters, that would also be a palindrome. So now we can easily get like a test to prove if it's a palindrome just based on the two, like if you remove the two characters, the inner string. So we can say let pal ij denote like if it's equal to 1 if the string from I to j is a palindrome. So if we have like if you have calculate like the way we calculate the states in this problem is we go in increasing order of length. We first calculate this dp for all small lengths of strings and then to the bigger one. So when we are calculating for pal ij, we will definitely have the necessary information needed because we are only considering smaller strings compared to it. So the condition is pal ij is 1 if si is equal to sj and pal I plus 1 and j minus 1 is also equal to 1. So basically what this is telling is a string from L to R is a palindrome only if the first and last letter they are equal and if the inner string is also a palindrome. So this is very nice. Now the each transition is just like the pal part is just O of 1. But the problem is asking how many substrings of a string are palindromes. So this part is required in the question, that is why I explained it now. So now let us denote dpij, that is the actual problem that we're trying to solve here, is the number of palindromes in string L to R. So the transition, as someone pointed out, it is dp. Yeah, because whatever is a palindrome that is of the inner string will also be a palindrome of like a substring. That substring will also be considered a palindrome for the outer string. So this would be dp of I plus 1 j minus 1. But can someone also point out the two other transitions that are required? Like what would not be included in dp I plus 1 j minus 1, but it can be a palindrome. Like that might be considered in this but not in this. Okay, I'll just tell the answer. One case is of course if the character si and sj are equal, then you're adding a new palindrome. That entire substring L to R is a new palindrome. So that I'll add it at the end here. That's kind of an obvious case. What this means is basically the entire string is a palindrome. So then you will add one. This is a boolean value. It's one if it is true and zero if it is not. And one other case most of you are probably missing is that in order to determine if this whole string is a palindrome, we have to check if this is a palindrome. But also we need to check for this string to here. Clearly that string is not contained in the dp of I plus 1 j minus 1, right? It is only a part of dp of I and j. So we need to account for that case separately, and it is quite easy. We have to just check if pal of that is true, and we will clearly have the pal values calculated before the dp values. So that would be how you handle this. So the number of substrings of that and that. But now you see that when you're adding this and then also this and this, there is an overlap here. So you're kind of double counting. You're kind of double counting, right? So then you would have to subtract. So you can use the like a very simple principle of inclusion and exclusion. You add that, and then subtract from whatever is there in the middle. So does this make sense? Like till now, whatever I said. Uh, See, you're considering this string, right? So and then you're saying the only transition is this to this, like L to R, then L plus 1 to R minus 1. But then do you also notice that there will, like, okay, I'll take in string itself. You have like for this string you're only considering this, but do you realize that this string might also be a palindrome? I mean, it might be, right? But this a b c d, this string is not considered in this smallest transition. Does that make sense? So you have to account for it. If this makes sense, just let me know. If you need more explanation, let me know. I'll explain. Can you tell me which case you're having a problem? The which case? Like I'm talking about L to R and then L plus 1 to R minus 1. Okay, I to J minus 1. Like, let me take some random string. For A to F, like let's suppose that AZXY might have also been a like the letters are not a palindrome here, but they might have been a palindrome, right? It might have been a palindrome. But it would clearly not be considered in if you're only considering this string in the transition, then AZXY will clearly not be considered, and so you're missing out on that case. Do you understand now? Yeah, and clearly again from the right side also you will do this something like this. Does that also make sense? L to R minus 1, R to L minus 1, but again you're like overcounting this. So basically you're again subtracting that. So what you said you were adding, you would actually subtract. Does it make sense? You would add the left end, right end, and then subtract the middle. And of course the final case where the entire string is a palindrome. So that is the DP transition here. Yeah, that was the problem. So I will quickly go through one more range DP problem. Do give this problem a try, and if anybody has any ideas, please do share them in the chat. I've sent a CSES problem in the chat to open it. This is also a standard problem at CSES, like a very standard range DP problem. It's a very good introduction. And it's a nice, like if it's the first time you're seeing such a problem, it's a nice problem to try. So I'll give you some 2-3 minutes to try the problem. If you've done it in the past, I can suggest another problem. I don't know if I'll be able to discuss it, but it's a nice problem. You can give it a try. Kind of similar, but little on the harder side. Do try this problem. And if you have done it, you can share your solution. What exactly does your DPIG mean? No, like it can also mean like if person one is starting there or person two is starting there, or just solving for a general game where a person start there, right? Okay, difference of the score. Okay, that's a good idea. And if people have already done this problem, you can try the other problem that I've sent. It's slightly more challenging, but very similar though. Okay, I'll present the solution for this. It's a standard problem, but the key idea is that for like normally you would think that you would store the score of any player in DPL2R. Such that if you place optimally, like DPL2R means the answer for the question only considering the range L2R. Like the array is just L2R. You solve the problem just for that, and you use the smaller ranges contained in it to compute the answer. But you would think that you would just score the score of the first person who's starting in this range, but that is not really helpful in the question. And the other thing that is helpful is the difference in scores. Basically, this is equal to the score of first player minus the score of second player. Now, using this as a state is quite helpful. And this is clearly something that you want to maximize, right? The person who's starting with this state from this L2R, he's starting the game from that state, will definitely want to maximize his score, like the difference of his score and the opponent's score. So the objective is just the problem reduces to maximizing this. Does that make sense? So this is what we're trying to solve now. If the game is started here, we want to maximize the person who starts from there. We don't really care about first or second player in the overall context. We're just focused on this part of the game right now. Yes, sum of the array plus TP divided by 2. Yes, because you have the difference. Can you tell me what kind of transitions do you have? The base case is just DP II is just AI because you can't really do anything. You have to take that whatever, like only one item is left in that array. Like basically, you're considering only an array of one element, so you have to take it, and your score will be that. And your opponent cannot really make a move, so he will have zero score. So your score minus zero is your score, like AI basically. So this is the base case. And again in this problem also, we do not really the order of calculating transition is we go from increasing size of subarrays. We calculate the answer for smaller subarrays, like literally every subarray of length 1, then every subarray of length 2, and that's how we go. Because clearly a range is dependent on the values of the smaller ranges. So by doing this, we can ensure that we can always calculate the value that we require. So now the transitions are dp. So now we are assuming that the player is starting here. So he only has two choices. He can either choose to take the leftmost item or he can choose to take the rightmost item. And let's say he chooses to take the leftmost item. Then in that case, he would get a score of A. Sorry, he will get a score of AL, but the opponent would now play the game on DP L plus 1 to R. So that difference would be subtracted from him. So you can see how this works. It's not that hard. Like now he has made a move, and then the opponent would now play on the array L plus 1 to R. So this is one of the choices that he has, or he could have taken the right element, and again the same thing would follow. Now the game will be played on DP L to R minus 1 by second player. Now that difference of scores will be subtracted from this to the player. Clearly the player wants to maximize this value, so he will take the maximum of these two. Does this make sense? If this transition makes sense to you, please let me know. Okay, so that's the problem, and so clearly now we want to solve the actual problem. The bigger problem is player one is starting on the whole range. So zero, sorry, depends on what base indexing you use. The answer can be dp 0 n minus 1, or if you use one base indexing, it is dp 1 to n. So this is the answer. So this was the problem on range dp. So now we will see one small segment, that is digit dp. So I'll just quickly go through a very small problem just to show you how it can be used, and then the lecture will be done. So digit dp, like, okay, I'll just end the problem. I'll just explain it with the problem. So all of you can take a look. It's also a CSES problem, a very standard problem, like a very standard problem of digit dp. The problem just says that you want to count number of integers between a and b which do not have any two adjacent digits same. So clearly, again, we extend our argument. Now the DP state do not have to just be an integer. Now we saw that they can be subsets of an array, or they can be continuous ranges. And here we see that they can be digits of a number rather than the number itself. The digits of a number are much lesser than the number. They're like a floor of log n base 10. So it is much lesser, and that is something that we can afford to iterate over. So in digit DP, the states contain the digits of a number. Basically, you do not consider number as a number itself, but it's decimal representation. Like you go through it like a string of a decimal representation. Does that make sense? It's analogous to the other two type of DP we saw. So we are just learning that states need not just be an integer or anything. They can be subsets, ranges, and digits. So for this particular problem, there are like a lot of tricky cases to handle. You need to keep track of a lot of information. And you can see that a and b are huge, like up to 10 to power 18. So you cannot afford to like go through these numbers and make any calculation. But the number of digits is limited. It can be at most 18 digits, which is quite small. You can do a DP on that. So the DP is, so actually right now it's not just less than b. You need to calculate from a to b. So I will now calculate a function f of b saying the number of numbers which satisfy that condition, no two adjacent digits are same, that are less than or equal to b, and f of a minus 1. Now the answer is just f of b minus f of a minus 1. Like it's very similar to prefix sums. What I can calculate using my DP is that I can calculate f of b, that is basically from 0 to b, all the integers which satisfy that. And I'll calculate that for 0 to a minus 1, and then I'll just subtract f of a minus 1 from f of b to get the required answer. Like I'll get the integer between a and b which satisfy the condition. So, so now we'll see about, I'll give you a rough idea on how to calculate f of b. There are a lot of states to keep in mind. So I'll just define the DP state. Let us say we're considering the position, like we're going from left to right. Let's say the digits are like this. The number, these are placeholders for digits. Let's say position is 1, 2, 3, 4, 5, and so on. So DP position, we're considering the position right now. What the previous digit was, we need to know that, because we can't repeat that digit again, right? We want the adjacent digits to stay different. So we need to have some information on what the previous digit was, so that we can make sure to not repeat it in this current position. So previous stores the digit in the previous position. Position is the current position we're considering. And we will have 4 states basically. So DP previous, then we will have to have leading zeros, because you notice that if the number can have a zero still now, let's say we're considering position number 4, position is basically 4. All these could have been 0 based on DP state, and this can also be 0. Like, technically we're actually repeating the digit here, but it is allowed because it is 0. It doesn't really matter. And since we're calculating for all numbers from 0 to b, clearly 0 will also be included, and even smaller numbers will be included. All of these need not be non-zero digit. They can have a sequence of zeros, and then the number can actually start. And in case if it is zero, then you have an option to make this also zero. That is what I'm saying. So we'll check if there are any, if there is a leading zero till now, then we have an option to make that the leading zero. And then there's one more criteria that I would call flag. Like I'm just calling it flag, but what flag essentially means is, since we are only considering less than or equal to b, since we are only considering less than or equal to b, like uh, we can't really go above b. Like we're also supposed to keep track of whether the current number we are actually considering till now. We can't just randomly choose digit. Just making sure that the adjacent digits are not same is not sufficient. We're trying to calculate those which are less than b. So we need to keep track. If everything till now is tight, like suppose the number, if let's say b is equal to 4536, right? And suppose, let us say this is, and we're considering the fifth digit. Suppose all the digits are exactly same till now, and the number is, let us say, 453678 or something like that. So now when we're considering this digit, we cannot put a 8 here, because clearly this number has to be less than b, right? Suppose this number was not exactly 45, then we had the freedom of putting any digit that we wanted. But since the number is tight till now, like it has every digit is exactly same, so we can't afford to go over the number b, because we're calculating f of b is clearly it has to be less than or equal to b. So then we have limited possibilities. We can only put 0 to 7. And if we put exactly 7 in the next DP state, we are calling the recursion, we will again set the flag tight is equal to true. The flag will be 1. So flag is basically a Boolean value which is saying if the number considered so far is exactly the same number, then we have to restrict ourselves. We can't really put any digit. It would be 0 to whatever the digit is present here, because we can't go over that digit. Otherwise, the number would exceed b. So are the DP states kind of clear? There's a lot to handle, like a lot of cases and stuff. But I think, like I've explained all the states. I think these states are sufficient for the problem. If you have any questions, you can ask. So position is the position of the number of digits, the ith digit that you're considering. Previous can be from 0 to 9, whatever the digit that the previous position had, so that you do not repeat that now. And now the transition is basically, you can choose any digit right now, and that will be the previous for the next transition that you are calling. And now if you had leading zeros till now, you can choose to add a leading zero even now, and then call the next recursion with a leading zero flag set to true. Both of these are Boolean values, and this flag represents whether the tightness of the number. Like till now, everything was exactly equal, so you couldn't afford to go overboard, like go above b. Is it clear? That's all the problem. Like, after that, you can just go through all the transition. Like you can just try all the digits from 0 to 9. Of course, it depends on the flag. You have some cases to handle based on leading zeros and flag. But for the general case, you just go through all the digits from 0 to 9. Then you can check if they work. They just don't have to be equal to the previous digit. Then you can call a recursive call to the next position based on this. Okay, if you don't have any doubts, I think that's it. This was the problem on digit DP. So the lecture is done. I'll post a problem set containing harder problems on the Discord group. If you have any doubt, you can ask.